Alright, calm. AQA A level chemistry, topic 2, completely patterned, yeah? The whole thing completely patterned, the amount of substance here. I'm also going to teach you water crystallization and also back titrations, everything, yeah? What these man on other YouTube don't teach you, you know what I'm saying? Alright, calm, let's get into it, yeah? So, relative atomic mass, yeah, and relative molecular mass, yeah? I've talked about this before in topic 1, yeah? Relative atomic mass is the mean mass of an atom of element divided by 1/12 of the mean mass of carbon 12 atom, yeah? Relative molecular mass is the mean mass of a molecule of a compound divided by 1/12 of the mean mass of a carbon 12 atom, yeah? So one of the atom and the other one is for the molecule, yeah? Obviously of the compound, yeah? So I've talked as to why it's carbon 12 atom in topic 1, but these are just two formulas, not formulas, definitions here that you need to know about, and that's the extent of it, yeah? Alright, calm. So the mole, yeah? The mole is an amount. So the same way how you got like a dozen means 12 in it. Yeah, you got few means three. Yeah. A mole is just an amount, yeah. You can have a mole of anything, yeah. You can have a mole of houses, mole of flats, mole of whatever, yeah. So a mole is just 6.022 times 10 to the power of 23 particles, yeah. So this is known as Avogadro's constant, yeah. So Avogadro's constant is a mole amount of things, yeah. And to calculate moles, yeah, you just do the mass in grams, yeah, divided by the mR, yeah. It's very easy, yeah. Alright, calm. Ideal gas equation, yeah. So there's certain laws, yeah, that basically connect pressure, volume, and temperature, yeah. And so essentially, yeah, you can connect them into an ideal gas equation that works, right? And so pressure has to be in Pascal, volume has to be in meter cubed, temperature has to be in Kelvin, yeah. Moles has to be N has to be moles, yeah, obviously. And then mass is in grams, yeah. And R is called the ideal gas constant, yeah, and that's just 8.31. It's always the same number, yeah. Calm. This is very easy, yeah. Empirical formula. Empirical formula is the simplest whole number ratio of atoms, yeah, of each element in a compound, yeah. Molecular formula is the real amount of each atom in the molecule, yeah, and it can be determined using the MR of the empirical and the true MR. So the empirical might be CHO, yeah, whereas the molecular one might be C6H6O6. You see what I'm saying? The true amount of each element, right? So use the true MR and then the empirical MR. The empirical MR will always be smaller than that true MR, and that tells you the scale that you have to times it by, right? Because it's a ratio, so the ratio can be like times by anything, yeah, to to go up to the real amount, right? So let's look at a question, yeah, so you can actually understand it, yeah, because I could just give you that definition doesn't mean anything, yeah. You need to actually know what it means in it. So here, yeah, I got a compound, yeah, which is 52.14% carbon, 13.13% hydrogen, yeah, and 34.73% oxygen by mass, yeah. Find the empirical formula. So these are percentages by mass. So deep it, if the 100% is the 100% mass, yeah, then 52.14 would be 52.14 of that 100%. So instead of having these as percentages here, I can just call them grams. It's the same thing. Do you see what I'm trying to say? So it will be 52.14 grams of carbon, yeah, 13.13 grams of hydrogen, and 34.73 grams of oxygen, yeah. You're allowed to just do that straight up, yeah. So now, again, it's my handwriting, allow it, yeah. Alright, cool. So what you need to do, yeah, is you need to find the moles of each one. So carbon, yeah, is 52.14 grams, yeah? You just convert percentage directly into grams, yeah? So 52.14 divided by the mR of carbon, or AR of carbon, yeah, which is 12. So 42.14 over 12 is 4.35, yeah? 13.13, the percentage of hydrogen, yeah, divided by the AR for hydrogen, which is 1, gives me 13.3, yeah? 34.73, percentage of oxygen, divided by 16, which is the mR of oxygen, AR of oxygen, gives you 2.2. So now I've got the moles. Now, after I got the moles here, you need to do something called a mole ratio or a mole fraction. What you do is you divide them by the smallest number. So what's the smallest number here? The smallest number here is 2.2, yeah? So these are the real moles. I want to find the smallest ratio. So I need to divide each one by 2.2. Does that make sense? So divide 4.35 by 2.2, I get 2. Divide 13.3 by 2.2, I get 6. Divide 2.2 by 2.2, I get 1. So now the empirical formula, therefore, would be C2H6O. So this is very, very easy, yeah? Make sure you know this, how to calculate empirical formula, yeah? If it gives it to you in grams, that's it, it's grams pattern there. If it gives it to you in percentage, you just directly change it into grams. That's the extent of it. It's very easy, yeah? Alright, calm. Percentage yield, yeah? Now, again, this is very easy. You have a question, you'll see it in the sheets when you watch the sheet video. And you'll see, yeah, percentage yield is just the experimental mass, so it'll tell you the experimental mass here, what the Don actually got when he did the experiment, yeah. And then you'll find the theoretical mass here using moles and whatnot and concentrations and whatever. It'll be very easy. And then you just do the experimental divide by the theoretical times 100, and that gives you the percentage yield, how much he made relative to how much he could have made, yeah. Atom economy works in the same way. You do MR of desired product, which is basically, the MR of the desired product, right? So you're gonna make maybe two products here, and if you make two products, one is desired, one's undesired, yeah. So you take basically how much shit is in the desired, and you divide it by the total amount of reactants that you had. That tells you, yeah, the ratio of how much like useful thing you made compared to like how much of the building blocks that there was, yeah, which tells you how much of the building blocks was wasted. Does that make sense? So this is even easier. This one you just find the MR of the desired product, divided by the MR of all the reactants, and that's it times by 100. Easy pattern, yeah. Calm. In industrial processes, yeah, it is desirable to have a high atom economy, so there is little or no waste product here. Hence, the process would be more economically viable for an industrial scale. It is also beneficial for the environment, yeah. Man, us man are all about that green planet, whatever the fuck. Alright, cool. So a student, so again, okay, here. This is water of crystallization, yeah? So these are a bit techie sometimes, yeah? You see them in the test, you might think, oh, damn, 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 you know what I'm saying? Not a lot of men know how to do this, yeah? But it's very easy if you break it down, yeah? So let's look at this, yeah? So a student heated a solid sample of Na2CO3 and XH2O, yeah, for 1 minute to remove water and determine a value for X. So it's hydrated and he wants to evaporate that water, yeah? The diagram shows the apparatus used here. The table shows the results recorded here. Mass of empty evaporating basin is that much. Mass of evaporating basin and solid before heating, so the hydrated version is 25.47, and then the unhydrated, dehydrated here, after evaporated is 24.92. So use the values in the table to calculate value for x, yeah? Calm. Easy. What you want to do always in these questions, yeah, find the mass of the actual water, yeah, and find the mass of the actual compound, yeah, so the actual Na2CO3, yeah, and then you can work out a ratio. So let's do that then, yeah. So mass of H2O, or deep it, yeah, this is easy. If something has water on it, yeah, and then I heat it and the water goes, it's gonna lose mass in it. It's gonna weigh less, yeah. So therefore, what I do, yeah, is I take the mass of it with the water, which is before heating, and I take away the mass after heating. That's gonna tell me the mass that was given off, which is the water. So that's 0.55 grams. Easy. Yeah? Before heating, after heating. Bang. Gives you the thing, yeah? Mass of Na2CO3, yeah? Well, deep it, that's not hydrated, that's just Na2CO3 alone, right? So the mass of dehydrated, just normal Na2CO3, yeah, is 24.92. But that's with the basin, yeah? The basin alone is 24.35. So I need to take away the mass of the basin, yeah? So now it's going to be 0.57 grams, yeah? Very easy. Now I've got the mass of Na2CO3 and I've got the mass of H2O, yeah? Calm. So now what I can do is I can find the moles of both of them. That's what you do. In chemistry, if you don't know what to do yet, and like in a math question, yeah, just find the moles, bro. You always get marks for that, yeah? Just find the moles in it. So calm. Let's find the moles, yeah? By the way, N means moles, yeah? So N, you could put bracket Na2CO3, that means moles of Na2CO3, yeah? So the moles of that, yeah, is 0.57, the mass, divided by the MR, yeah? MR, you can find that from the periodic table, yeah? For this compound, it's 106. So that gives me 0.0054 pattern. Next one, yeah, is the moles of water, yeah? So N of H2O, the MR of H2O is 18 and the mass was 0.55. So you do that, you get the moles of H2O is 0.0306. Now again, you do that same mole ratio, mole fraction, whatever you want to call it, yeah? Where you divide it by the smaller one. So you divide 0.0306 by 0.054. So dividing that by that gives you 1, and then dividing that by that will give you 5.67. So therefore x, yeah, is 5.67. For every 1 mole of Na2CO3, you got 5.67 of water. That's the question. For every one here, you got that x many of that, yeah? So that's it. It's very easy, yeah? Very easy. So trust me, yeah, it might look hard, yeah? That was 5 marks, by the way. So honestly, yeah, it's pattern, man. Come on, yeah. Maturing is realizing that this is easy, innit? You know what I'm saying? Yeah, don't worry, man. Man, say it's a pattern, you don't worry. Calm. Back titrations, yeah. Again, another term that invokes fear in the man, them, yeah. So let's look at this, yeah. So this can get a little bit more complicated, yeah, but really and truly, it's nothing, you know. So an indigestion tablet, yeah, was crushed up as a tablet, yeah, and an excess of hydrochloric acid of that much, yeah, is added. The resultant solution was titrated against that much of NaOH, requiring that. So for any question like this, yeah, just break it down, man. Understand like wagwan, you get me? Yeah? You got a tablet that you put in bare hydrochloric acid, yeah? Then that resulting solution of whatever reaction dissolving will happen there, yeah? You then titrate that with a, to cause a neutralization reaction with the NaOH, yeah, with the base, yeah? And the amount of base that you needed was that amount of base. Calm. So now you want to calculate, yeah, how much like calcium carbonate was actually in that tablet originally. So just reverse it. So the final step was we titrated it, right? So calm. I have the measurements for NaOH. I want to find how much HCl was used. If I can find how much HCl was used, I know how much the I mean like final, right? So how much HCl was combined with NaOH, yeah? How much was actually titrated, right? And if I find how much was titrated, and I can also find the initial hydrochloric acid here, because it gives me these measurements here. So if I can find the original and the after, then I can find how much was used. And if I can find how much was used, the used is the thing that reacted with the calcium carbonate. So if I can find how much was used, I can find how much calcium carbonate I had, yeah? And that's the question done, basic, yeah? So let's find the moles of NaOH first, yeah? Again, if you don't know what to do, just find the moles, bro. That's the easiest thing you can do, yeah? So, I've got 25.8 cm cubed of this thing, yeah? Of sodium hydroxide, yeah? That's a sodium carbonate earlier. It's tweaking, fam. Alright, cool. So, sodium hydroxide, yeah? So, you divide, yeah, the cm cubed by 1000 to get dm cubed, yeah? Easy. And then moles is equal to concentration times the volume, yeah? So I got the volume in dm cubed and I just times it by the concentration, yeah? 0.500, yeah? And now I got the moles. Easy. Now, that's the moles of NaOH. I need to find how much moles was combined with HCl, yeah? So how many moles of HCl I had, yeah? Well, I need to know the ratio, yeah? So either you can balance the equation or a quick method to do it, yeah? Is what makes the HCl an acid, yeah? Inherently, is the H plus in it, yeah? And what makes this an alkali is the OH, yeah? Now, what's the ion for the OH? It's a negative one ion, yeah? What's the ion for the H? It's a plus one ion. So therefore, if this is plus one, this is negative one, then it's going to be 1-to-1 ratio, yeah? Easy. So N of HCl would also be the same amount, 1-to-1 ratio, yeah? So 0.0129, yeah? So it's just the same ratio, bruv, yeah? Easy. Now, how much HCl did I actually use at the start, right? Before the reaction happened, how much was there, yeah? Well, it tells me 25 centimeter cube of 1 mole per dm cubed. So 1 concentration times 25 over 1000, yeah? Because that's dm cubed, yeah? So 1 times the volume, concentration times volume, gives me the mole at the start, which was 0.025. So if I got the moles after, and I got the moles before, I can find how much was used, or how much actually reacted, yeah? So 0.025 minus 0.0129. That gives me how much was used, 0.0121. Basic maths, yeah? So, recap here. I found how much NaOH was used in the titration, yeah? Then, based on that, I know how much HCl was in the titration. And then, based on that, and then what I did is I found the initial amount of HCl that was that the tablet was dissolved in. And then what did I do? I minus the initial from the after to find out how much was actually reacted, how much was used to make the product. Because HCl and the calcium carbonate would have made a product, right? So that HCl would have been lost, right? And that's 0.0121 that was lost, yeah? So now that I know how much was actually used here, I can now see how much calcium carbonate because I know it reacted with that. So again, using the same techniques here, CaCO3 and HCl, yeah, I want to know what the relation is here. Easy. So CO3 is what ion? 2 minus. That's what the CO3 makes it an alkali, yeah? So CO3 is 2 minus, yeah? And acid is H plus. So easily, yeah, that means I need two H pluses to come to neutralize the CO3, 2 minus it. So 2-to-1, 1-to-2 ratio, yeah? So that means that if I've got 0.0121 moles of H plus of HCl, yeah, I need to divide this by 2 to get how much calcium carbonate. So just divide that by 2. Now I got the moles for calcium carbonate, yeah? Easy. And then final step here, moles is equal to mass over mR. So mass is equal to moles times mR, yeah? And the mass of calcium carbonate, therefore, is the moles, which I just found now, 6.05 times 10 to the power minus 3, yeah? Times the mR, which is 100 roughly, yeah? I think it's 100.1 or something, yeah? About 100 basically, yeah? Times these two together, you get 0.605 grams. So that's it. That's the most. Pattern, easy. You see what I'm saying? And that's literally the end, yeah? It's actually not hard, yeah? I'm gonna do the sheets as well so you can see that, yeah? But it's actually basic, man. Yeah? You, man, don't get caught up in this chapter because I know in year 12 that's the hardest chapter, probably, yeah? Is this little one here, yeah? But it's not really, you know what I'm trying to say, yeah? So, anyway, yeah, that's about it, you know?